Hello friends, welcome to a new video where I'm planning to solve this problem from GATE 2015. So this is a very interesting problem, I would say. So here we have a pinion shown here, then we have all the properties of this particular pinion is given here. It is of radius r, its inertia is given. What we are actually doing here, you can actually read the question. You can pause my video for a while and then you read the question first, then understand what they are actually asking us to find it out. So pause the video for a while and then come back. Okay, now I hope you have read the question at least once. So here we have a pinion which is driving a gear. The large one is the gear, pinion is the small one. We are applying a torque one in the pinion, so it is rotating in the clockwise direction due to the torque applied on it. Then obviously the gear will rotate in the anti-clockwise directions. Then theta 1 and theta 2 are the angular displacement. Now they are actually asking us to come up with a set of equations which will be applicable, which will be true in this case. So if you observe the options very carefully, you can see almost all options have a relation connecting F1 and F2, which are respectively the forces felt by each of these individual objects at the point where they interact with each other. Basically these two are the free body diagrams. So what you can tell about F1 and F2, this is pretty obvious. This comes from Newton's second law. Since these two bodies are in contact by Newton's second law, whatever, let's say my pinion is applying a force on the gear, then an equivalent opposite force will be felt by the pinion. So F1 should be equal to F2. See, here you have to pay attention. This is not a vectorial representation. In vector it should have been F1 vector is equal to minus F2 vector. But the direction is already shown in the figure. So F1 and F2 are basically the magnitude of these forces, because the direction sense of these quantities are already taken care by the direction of these arrows. One is pointing upwards and the other is pointing downwards. So F1 and F2 basically denotes the magnitude. Now let's go ahead. Now let's try to come up with a set of equations. Or is it the other way around? Then I will just modify this. If it is the other way around, then like I will draw, I think it is the other way around. So let's say I'm applying an external torque like this. Let's say this is the point at which these two things are coming into contact. Okay, fine. This is of radius r2 and this is of radius r1. Let's say this is f. Now f is only one f. There is only one f. We don't have to talk about so many f because that was the first point. Now the key concept whenever you analyze gears or two bodies in contact is that the point of contact, let's say at the point of contact, the velocity should be same. Let me elaborate it a little bit. So think of pinion rotating as alone. let's say this is rotating with an angular, this small pinion is rotating with an angular velocity of theta 1 and this one is rotating with the angular velocity of theta 2. And let's say this is the point P where it comes into contact. Now when it comes into contact, these points are one point, like these 2 points will merge into a single point. So if we compute the velocity of the point P, considering it as a point in body 1 or in pinion, the velocity will be given by r1 theta 1 dot. Similarly, if we consider the point as a part of the body 2, then the velocity will be given by r2 theta 2 dot. These both should be equal, then only we will have a smooth functioning, otherwise there will be slip. I am not getting into the details of those stuff. So this is a basic criteria that should hold. Make sense? Okay. Back to the now. Now, if I write Newton's equation for the first pinion, then I1 theta 1 double dot, let's say theta 1 dot is positive, theta 1 is positive in this direction, okay, then I1 theta 1 dot will be equal to tau minus, this is our force F into R1. Similarly, if we write, let's say this is the theta 2 direction and I2 is this is our F, okay, this is our F. I didn't draw it vertically. Let's see, let's make it much more clear. So this is vertical force, this is the same force, this is the force applied by the pinion on this thing. Then if I write Newton's law, then it will be I2 theta 2 dot double dot is equal to, this is my F times R. Okay, so from this equation F can be written as I2 theta 2 double dot divided by R2. But from the previous slide we established that if there is a point P here, the velocity of both these points should be the same, and then we established R1 theta 1 should be equal to R2 theta 2 dot. If you plug in this equation here, if you plug this equation here, then this will be I2 R1 theta 1 double dot divided by R2. So now we have a definite expression for F. Now plug it here, plug this one here. Now we will get I1 theta 1 double dot is equal to tau minus I2, then R1 square, R2 square. Let me erase this arrow. Cool. Times theta 1 double dot. Now tau is taking this term to the left side. I1, okay, I will take all those terms together. It will be I2 R1 square divided by R2 square theta 1 double dot. Make sense? So coming back, there are two options. Since the gate being an objective examination, we can actually rule out two of these options in the first guess itself. So now we have to only pick among the two. all we are ruling out the other rest of the two. First slide, this seems to be the answer. In the first look this seems to be the answer, but once we implement all the concepts step by step, two concepts, one is Newton's third law and the other one is applying Newton's second law to each of those bodies, keeping in mind that when two things are in contact, at the point of contact velocity should be the same. So implementing these two concepts, we can rightly pick this particular answer. Thanks for watching.